We'll be discussing what de Laval's nozzle is, Mach numbers, proof of the nozzle using Bernoulli's, and Mach diamonds.
Gustave de Laval invented a nozzle that could produce supersonic exhaust and is currently applied to rocket engines, and the nozzle was named after him, called the de Laval nozzle. It consists of a converging section, a throat, and a diverging section.
Producing supersonic exhaust makes the engine extremely efficient. In fact, the de Laval nozzle is one of the most efficient engines known to man.
Since de Laval is concerned with high-speed flight, we have to understand Mach numbers. A Mach number compares a body's speed to the speed of sound. If a body is moving at Mach 1 speeds, it's moving at the speed of sound. If a body is moving at Mach 2, it's moving at twice the speed of sound. Mach 0.7 is 70% the speed of sound, and so on.
At subsonic speeds, gas can be modeled using continuity, so velocity increases in the converging portion of the nozzle. However, at sonic and supersonic speeds, gas no longer behaves like incompressible flow, and continuity no longer applies. This means that the throat never reaches speeds past Mach 1, and gas can only make a transition from subsonic to supersonic speed at the throat of the nozzle. Next, we'll see how Bernoulli's proves that the diverging section of the nozzle produces supersonic speeds. At this point, you may be wondering why supersonic speeds allows velocity to increase with area, which goes against our original conceptions of continuity that we learned in class, where area times velocity in one end of a tube will equal to area times velocity at a second location. However, recall that this rule only applies to incompressible fluids, and gas exhaust is compressible, so the continuity equation does not apply here. Although continuity isn't applicable, Bernoulli still is. So let's bring up Bernoulli's equation to explain how this phenomenon is possible at supersonic speeds. Looking at the de Laval nozzle, the height is constant as the area changes. So h is equal to 0 and rho gh is equal to 0. And that leaves us with pressure plus half rho v squared is equal to pressure at the second point plus half rho v squared. Since gas particles can't materialize from nothing, we also know that there is a constant mass of gas particles across the whole nozzle. And recall that the equation for density is equal to mass over volume, and in this situation, mass 1 is equal to mass 2. On the other hand, volume changes, and the volume is smaller at the converging section than at the diverging section of the nozzle, so volume 1 is less than volume 2. The effect this has on the density of the gas is that the density at the converging section of the nozzle is greater than the density at the diverging part of the nozzle. This graph shows the pressure in the de Laval nozzle system. The pressure is highest in the converging section before the throat and lowest afterwards, so we can say that the pressure at point 1 is greater than the pressure at point 2. Putting this all into Bernoulli's, we know that pressure and density at point 1, or the converging section of the nozzle, goes up, and the pressure and density at point 2 goes down. And so the velocity at point 2 goes up, and the velocity at the converging section of the nozzle must go down for Bernoulli's to be true. One consequence of the de Laval nozzle is a phenomenon called Mach diamonds. We should take a look at different types of flow. When the flow is overexpanded, the exhaust plume is pinched. And as you can see in this photo, this occurs because atmospheric pressure is greater than the exhaust pressure. However, at an optimum altitude higher up, the atmospheric pressure has dropped, and the exit pressure now equals the ambient pressure. Here, the nozzle is working at its maximum efficiency. As you move up to a higher altitude, atmospheric pressure has decreased further, and exit pressure is now greater than ambient pressure. So this reduces efficiency since some of the force being generated by the exhaust is not pointing in the exact opposite direction that we want the rocket to go in. When supersonic exhaust is exposed to the atmosphere and is over or underexpanded, a standing shock wave called a Mach diamond forms. If you were to begin with overexpanded flow, that means that the total pressure of the exhaust is lower than the atmospheric pressure. As the flow compresses, the exhaust pressure surpasses atmospheric pressure, and the flow expands outwards. As the flow's diameter increases, the velocity slows down and turns inward again because the pressure of the exhaust decreases. And this process repeats over and over until you get something that looks like this. This is a video of SpaceX's Raptor engine test.
Even though the de Laval nozzle seems to break the laws of physics at first glance, through applying Bernoulli's principle, we can see that the nozzle ingeniously harnesses fluid dynamics and the laws of supersonic speed to accelerate rockets and planes to incredible velocities. This high-speed flight is not only important for technological and scientific advancements, but creates the beautiful structure known as Mach diamonds, lighting up both our future and the sky.